Hi friends, we would like to understand shear force diagram and bending moment diagram with the help of an example. So before starting, let's understand what is the definition of shear force diagram. So shear force diagram is a graphical representation of the variation of shear forces at every point over the entire span length of a beam. We find shear forces at every point of the beam and draw its graph. So it is a graphical representation of variation of shear forces at every point over the entire span length of the beam. And similarly, we have bending moment diagram. So bending moment diagram is the graphical representation of variation of the bending moments at every point over the entire span length of the beam. So we calculate shear forces and bending moments at every point over the entire span length of the beam, and we plot the graph, and that variation is called as shear force diagram and bending moment diagram. Okay, this shear force diagram and bending moment diagram will be more clear as we go along, but before that, let's understand what are the steps to draw shear force diagram and bending moment diagram. So we'll try to understand stepwise. So we will take one example because we are learning through an example. Okay, so we will take an example of a beam, and through that example we'll try to understand the various steps to draw shear force and bending moment diagram. So let's see what are the various steps. So the first step before drawing any shear force and bending moment diagram is to draw free body diagram of a beam. So let's take one example of a beam. So we have got a beam here AE, and there are points B, C, D in between, and this beam is having hinge support at point E and the roller support at point A, and there are loads which acts at point B, 150 kilonewton which act at point C, and 100 kilonewton act at point D, and distance between AB, BC, CD and DE are taken as 1 meter, 1 meter, 1 meter, 1 meter. Okay, so I have taken a simple example. So the first step, as it is mentioned here, we'll draw free body diagram. So let's draw free body diagram here. So as we know that while drawing free body diagram, we make a beam free from all supports. Okay, so we have got a beam here. So the forces acting on the beam are as it is mentioned here. So we will have a support reaction at point A, RA. Since it is a roller support, you can see here, so it will be having only single vertical support reaction RA. And similarly, because point E is a hinge support, it should have two reactions. One is in vertical direction, another in horizontal direction. But we can see here there is no horizontal load acting on the beam, so there won't be any horizontal reaction at point E. So we will have only vertical reaction, which is RE, which is acting in the upward direction. Okay, so this is basically a free body diagram. So what we have done in free body diagram, we have made the beam free from all its supports, and at the support points we have given the support reaction. Okay, so we have got support reaction RA at point A and support reaction RE at point E. Now, so this is the first step, draw free body diagram. Now we'll see the second step. Let's understand the second step to draw shear force diagram. And the second step to draw the shear force diagram is to calculate support reaction. So we have got free body diagram of the beam, and there are two support reactions. One is RA and the second one is RE. So we have to find the value of RA and RE. So that is called as to calculate the support reaction. Now to calculate the support reaction, we have to follow the condition of static equilibrium. Now what is the condition of static equilibrium? So let me explain you the condition of static equilibrium. So the condition of static equilibrium is summation of all horizontal forces, summation of f of x equals 0, summation of all vertical forces acting on the beam, summation of f of y equal to 0, and summation of all moment of forces about any point, or you can take any point here, equal to 0. So these conditions are called as condition of static equilibrium. Now, as we know that there is no horizontal force acting on the beam, so this condition will be ruled out. So we will not follow summation of f of x equal to 0. So the remaining condition will be only this much, that is summation of vertical forces acting on the beam equal to 0 and summation of moment of forces about any point of the beam equal to 0. So let's take one by one. So we'll first take summation of f of y. So we'll take first condition summation of f of y equal to 0, and later on then we'll take summation of moment about a point of the beam equal to 0, and then we'll calculate RA and RE. So let's see the procedure. So we are going to follow summation of f of y equal to 0. Now when we do summation of f of y, it means sum of all vertical forces equal to 0. So we have vertical force RA. RA is acting in the upward direction, we have vertical force RE which is acting in the upward direction. So RA and RB I am going to take positive. And similarly, these three forces acting on the beam are acting in the downward direction. So I am going to take them negative. So let's see how to write down. So we have RA have taken positive. Then we have RE, that is also taken as positive, minus 100 acting downward, minus 150 acting downward, minus again 100 acting downward, equal to 0. So these three forces have taken negative, while these upward acting forces have taken positive. A very simple sign convention. So if you simplify this, you can bring this all negatives to the right hand side of the equality sign. So we'll get like this: RA plus RE equal to 100 plus 100, 200, 200 and 150, 350, 350 kilonewtons. So this is the first equation we got. So we can just name it as first equation so that we can later on use it. So from first condition, that is summation of forces equal to 0, we got RA plus RE equal to 350 kilonewtons. Now we have got the second condition, summation of moment of forces. So I am going to take moment about point A. You can take any point, you can take point A, point E or any point, but we should always take moment about a point where you want to find the unknown quantity, because I want to find RA, so taking moment about point A will be easy. Similarly, I can take moment about point E also, because there is unknown force R is acting at that point. If you take moment about point B, C and D, it will be, you can easily find the solution, but it will be a little bit of complication. Okay, so I would always advise you take the moment about point A where unknown force is acting. Okay, let's see how it will be easy. So when I take moment about point A, the moment due to RA will be 0 because RA is acting at the same point. So there won't be any moment caused by force RA. So moment will be caused by 100 kilonewtons. So 100 kilonewtons acting like this, and its distance from point A is 1 meter. So 100 into 1, and because of this is going to cause this kind of moment, that is called as clockwise moment. So 100 kilonewton will cause clockwise moment. 150 kilonewton also will cause clockwise moment like this, and 100 kilonewton, this one will also cause clockwise moment like this. Okay, so I am going to take all this clockwise moment as positive, and similarly RE is going to rotate beam in this direction anti-clockwise, so that is anti-clockwise moment. So all clockwise moments we shall be taking positive. So this will be positive moment, so this will be positive moment. This, the moment by 150 kilonewton will be also positive. This will also be positive, while the moment caused by RE will be negative. Okay, and the moment by force RA will be 0 because it is acting at the same point A. So we'll write down that. So 100 into 1 meter, 100 kilonewton is the force, and this distance from point A is 1 meter. So 100 into 1 meter. Again, moment caused by 150 will be 150, and the distance is from point A, and distance from point A is 2 meter. So it is 150 into 2. Moment caused by this 100 kilonewton will be 100 into, and its distance from point A will be 3. So 100 into 3. So we got moment from all these three forces. Now moment caused by RE will be RE into distance from point A will be 4. RE into 4, and that is going to be 0. So if you simplify this, you will get 4 times RE will be equal to, so it is going to be 100. 150 into is 300, and 100 into 3 again 300 plus 300, and if you add this up you will get 300 plus 300, 600 plus 100, that is 700. So 4 RE equal to 700, and if you simplify this you will get the value of RE as 700 divided by 4, and that value will be 175 kilonewton. So here we got the value of, so this I can call as equation number 2. So here we got the value of support reaction at point E. To calculate the value of RA, we have to calculate the value of RA. So if you substitute the value of RE in equation 1, so we know RA plus RE is 350. So if I put RE equal to 175, the value of RA will be also 175. So we got the value of RA as 175 kilonewton. And similarly, already we have got the value of RE. So value of RE is 175. So you can see here in the step 2, we have calculated the support reaction by using condition of static equilibrium. So now we'll see what is the step 2. So let's go ahead and understand the step 3 to find shear force and bending moment diagram. So friends, now we have the step 3 to calculate shear force at salient points. Now in the step 3, what we do is, once we got all the support reactions, we go for calculation of shear forces at salient points. We have got this beam, you can see here, and in this beam we got all the forces acting on the beam. Now the question is how to calculate the shear forces at salient points. So if you look at the diagram, these points which are point A, point B, point C, point D and point D, these are called as salient points. Now how to decide which points are salient point? Wherever there are forces acting on the points, those points are called as salient points. Okay. So what is shear force? So shear force is basically a transverse force acting at a point of the beam. So this RA 175 is acting is a transverse force and it will try to create shearing action at point A. So RA is a shear force. See, 100 kilonewton is a shear force. So I have already covered shear force in the previous lectures. Kindly go through the basic understanding of shear forces. So all these transverse forces, you can see 175, 100 kilonewton, 150, all are acting perpendicular to the length of the beam. So it will try to shear the beam, and that is why these forces are called as shear forces. Now to understand the variation of shear forces, first of all we have to go for step 3 and calculate shear forces at salient points. So salient points I have already explained you. All the points where the transverse forces are acting are called as salient point. So we have got 1, 2, 3, 4, 5 salient points. Okay. Now if you see here, just before this particular point A here, if you see at this particular section, and just after this particular section A, before and after, if you see, so if I start from this particular section and I move towards right, so at this particular section there is no shear force acting. Okay, you can see here, but as I cover this particular point A, this particular shear force RA is going to come into the picture. So similarly we'll further move towards right and just before point B. So if you are just before point B at this point, so you have only covered one shear force, that is 175 kilonewton. Okay. So as you go towards right at this particular section, you will be covering this one upward shear force 175 kilonewton and one downward shear force 100 kilonewton. So the effect will be 175 minus 100. Okay. So like that we will be moving towards from left to right. Okay. And we'll try to cover all the shear forces acting on the beam. You can also move from right to left also. For there we have to follow different sign convention, which I have already explained you, and some part of that also I will explain here. So let's see how to proceed further. So for shear forces we have got a sign convention. Kindly understand. We are going to consider a section, for example, and if your force is towards left hand side of this particular section and it is acting upward direction. So in the left side of the plane, upward shear force is taken as positive, and the left side of the plane, downward shear force is taken as negative. So kindly understand this. Similarly, from the considered plane, if the force is at right hand side and it is acting downward, it is taken as positive. And similarly, if the force is towards right hand side of the plane and it is acting upward direction, it is taken as negative. But we are going to follow this particular method where your plane is going to be towards right, because we are going to move from point A to point E. So always forces are going to lie on the left hand side of this particular plane. Okay. So we'll be moving from point A to B and we'll try to see how many shear forces are going to come at the left of this particular section. Okay, so we'll follow the first one, which is the force is going to be in the left hand side of the given considered plane. So if it is upward, it is taken as positive. If it is downward, it is taken as negative. So let's proceed further and see. So I am going to start from point A, but just before point A, I am going to take a plane like this. So this plane I am considering, and I am going to take all the forces acting to the left hand side of this particular plane. So if you see here, at the left hand side of this particular plane, there is no force acting, no shear force acting. Okay, clear? So I am going to consider all the forces which are acting at the left hand side of this particular plane XX. So if you see here, shear force at point A, when your plane is just left side of this particular point A, so just left of the point A, at that condition we don't have any shear force acting. So we can say that it is going to be 0 kilonewton. Now we'll take this particular plane just right of this particular point A. So now you can see that this is the plane XX. Now it has covered a vertical shear force of 175 kilonewton. Okay, so we can write down shear force as, because it is acting upward direction, so as per this sign convention it is going to be positive. So it is going to be plus 175 kilonewton. So it is acting in the upward direction. Now I will take this plane further till left side of this particular point B. So just left of the particular point B, because I want to cover all the shear forces acting from here to here. My plane is just left of the point B. Okay, so shear force at point B just left. So we are keeping our plane just left hand side of this particular point B. So now if you see, the force covered is only this force, there is no other force has come into the picture. Okay, that means there is no variation of shear force in this condition also, only one force acting in the upward direction, so it is going to be positive 175. Now we'll take this particular xx plane just right hand side of the point B and we'll see what is the condition now. So if you see this condition now, friends, we have got one shear force acting in the upward direction and one shear force acting in the downward direction, like this. Okay, so the upward, as per rule sign convention, upward to the left of the particular plane, there is a plane, and left hand side of the plane upward is taken as positive, and again the plane downward is taken as negative. So this is going to be positive and this is going to be negative. So what I will do is I'll write down the values. This is plus 175 and then minus 100. That will turn out to be 75 kilonewton. So we got shear force at point B just right, means at this particular point B, if you keep your plane just right of the point B, just you cover this particular point, then you got this upward shear force and this downward shear force, and the net value will be 75 kilonewton, which is positive, it means acting in the upward direction. Okay, so I got the variation of shear forces from point A to point B. Now I want to get to point C. So again this particular xx plane I will keep just left hand side of this particular point C, something like this. Now shear force at point C just left. So just left means we are going to keep our reference xx plane just before point C. So if you again see the situation, again we have force 175 kilonewton upward and 100 kilonewton downward. Only these two forces are there. There is no other forces come into the picture. It means the value will remain same as 75 kilonewton. So we can directly write down plus 75. Now we will move this reference plane xx to the right hand side of the point C. That is called a shear force at point C just right. So when you move it just right to the point C, it will be somewhere here, and now it will cover this shear force, this shear force and this shear force. So there are three shear forces, 175 upward and 100 and 150 downward. So you can simply see from here it is 175 minus 250, and if you simplify it further, this value will turn out to be minus 75 kilonewton. Okay, is it clear? The shear force at point C just right is going to be minus 75 kilonewton. Okay, now we would like to find the shear force at point D, at this particular point. So we will keep our reference plane xx just before point D, and then we'll keep it on just right hand side of point D. So let's see, when you keep your reference plane just left of the point D, your reference plane is going to be here, and if you see here, the forces covered are same as in the previous case. So same forces which were there in the previous case, right? The same forces are going to come here. So the value is going to be same as minus 75 kilonewton, because there is no other force coming into the picture. So now we'll move this reference plane just right of the point D, and that is called as shear force at point D just right. So it will be something like this. So here if you see, now this one additional force of minus 100 kilonewton is going to come into the picture. So it was minus 75 up to here, now minus 100 will come into the picture, and that will be, so I'll write down like this, minus 75 was there, and a new force of minus 100 kilonewton has come into the picture. So minus 100, so it will be minus 175. So the value is going to be minus 175. So I'll write down that minus 175. When your reference plane is just right of the point D, you got the shear force as minus 175. So if you add all these shear forces, you'll get minus 175. Now we'll try to see shear force at point D, just left and just right. So to calculate shear force at point E just left, it means your reference plane is at just left of the point E. Now if you see here, the forces covered are this force, this force, this force and this force, right? These four forces are covered. There is no other force has come into the picture, but the addition of all these forces has given us minus 175. Okay, in the previous case also it was same, so it will be minus 175. There is no new force has come into the picture, so it is same as minus 175 kilonewton. Okay, now we'll move this reference plane xs to just right of the point E. like this. Now when you go to just right of the point E, one additional force is going to come into the picture, and that additional force is this one. Okay, that is 175 acting in the upward direction. So upward means what? Upward means positive and downward is negative. So minus 175 plus 175. So the entire value is going to be 0 kilonewton. Mind it, always when you go just right to the point E, the shear force must be 0. And when you are just left to the point A, shear force has to be 0. Because now you are out of the beam and the beam is in equilibrium conditions, so all forces are balanced. So shear force has to be 0 kilonewton. This is a very important check. Okay. So always you have to check when you go out of the beam, there has to be no shear force. Here also, if you are outside the beam A, it was 0. You can see from here, right? So this also will be 0 and this also will be 0. That has to be 0. So we got the variation of shear forces starting from just outside the beam, that is left of the A, from point A. So we covered all the variation of shear force at every point of the beam. So what is the definition of shear force? If you remember, it is the variation of shear forces at every point of the length of the beam, right? So at every point, if you get the value of shear forces and you plot the graph, that graph is called as shear force diagram. So in that, we draw the variation of shear forces at each and every point of the beam. So here we have covered all the points of the beam. So now we can plot this variation of shear forces along the length of the beam, and that is called as step 4. Let's see the step 4, friends. We draw shear force diagram where we draw the variation of shear forces at every point over the span of the beam. This is a very important point to remember. Now in the step 4, we draw the shear force diagram. So we have got shear forces at the salient points of the beam. You can see here. So this is the free body diagram of the beam. We have already drawn that earlier. So what we do is we represent the beam and we represent all the forces acting on the beam. Now we want to get shear forces acting on the beam along its length at each and every point. So I have just marked all the points by the vertical lines. Okay. This horizontal line will be having shear forces on it. So I'll write down SF shear force diagram. So on this particular horizontal axis, you'll be getting the values of shear forces plotted. Okay, so we have got the point A, point B, this point I have shown here, point C again the same point D and point E. So what we do, we represent all the points on this axis. This is called a shear force axis. Okay, and now at point A, I'll be marking all the shear forces we got at point A. Point A, we have two shear forces, that is 0 starting from the left of the point A is 0 kilonewton. And at the right of the point A, it is 175 kilonewton. So we got one as 0 kilonewton, and the second one is 175 kilonewton. So this is 0 kilonewton, you can see, and this is 175 kilonewton here. So your shear force is increasing from 0 to 175 like this. Okay, from left hand side of the point A, there was 0 shear force, and as you cover point A, your shear force has gone to 175. That variation is shown by this particular vertical line. Now at point B, we have 175 kilonewton, same value, and at point B, if you just cross the point B, just left of the point B, we have 175 as you seen here, and as you cross the point B, you are getting just right, that is 75 kilonewton. So here it is 75 kilonewton. So your value will come down like this. Okay, so this is 175 as it is, but here it is 75 kilonewton because it has come down. So as you cross point B, 175 minus 100 will come as 75. So here we got 75. That is variation is shown here. Now I will go to point C. So point C, we have again 2 points, just left and just right. So just left of the point C is 75 kilonewton. The same value will continue. So you'll see straight line graph from here to here. So now this 150 Newton, if you move from left hand side of point C to right hand side of point C, is another force, that is minus 150 will come into the picture. 75 minus 150 will be minus 75, that is just right of the point C, you can see here. So it is going to be like this. So your shear force will vary like this. So minus 75 you got here. So this is the variation from left side of point C to right side of point C. Now we'll go to point D. So just left of point D is going to be same value. So from point C, from this point to this point, the shear force variation is going to be flat horizontal line. Okay, there is no changes in the shear force values. And if you go from left hand side of point D to right hand side of point D, you are getting further, there is a reduction of the value of shear force. it becomes minus 175 because there is additional 100 kilonewton negatives adding up. So minus 75 or minus 100 will become minus 175. So your variation will be like this. So shear force is increasing from point D left to point D right, okay, and becomes from minus 75 to minus 175 because this additional 100 kilonewton downward shear force is acting over here. Now we'll go to point E just left. So there is no other force coming into the picture, so same value would continue. You can see here minus 175, same value just left of this. And if you go to right of point E, this additional positive 175 will come. So minus 175 plus 175 will give you zero value, zero shear force at just right of the point E. So this is how we got here. So here it is 0. So the shear force is varying like this. It goes from 0 to 175. Point A, from point A to B remains 175. Then it goes down as you cross point B, and then it becomes 75. From B to C it remains 75. As you cross point C it becomes minus 75. C to D it remains minus 75. It remains minus 75, and then again if you cross point D it goes minus 175. From D to E it remains minus 175. As you cross point E it becomes 0. So this is the variation of shear forces, and the diagram representing shear force is called as shear force diagram. So this is a simple procedure we have to adopt while drawing shear force diagram. Okay. Now here if you see the shear force diagram which is above the axis is called as positive shear force, and shear force diagram below the axis is called as negative shear force. Okay. So this is positive shear force diagram above the axis, and below the axis it is negative shear force diagram.